We now go through a systematic discussion of the process you need to go through when drawing Lewis structures for molecules. And this is a crucially important skill in your study of chemistry. So a Lewis structure, by definition, is a drawing of the molecule showing the connectivity of all the atoms and the location of all the electrons. And electrons can be located either in bonds or in lone pairs. So the first step in drawing a Lewis structure is to know the number of covalent bonds that a particular element can form. So the general principle is that the number of covalent bonds is the smaller of one of two numbers. It's either the smaller of the number of valence electrons or the number of available orbitals for that element in the valence shell. And an orbital is available if it is empty or half-filled. So let's refer back to this diagram from a previous lesson. So as you can see, starting at the top, hydrogen has one valence electron. Its valence orbital is the 1s orbital, but that orbital is not completely filled. So therefore, it has one what we'll call available orbital. It's half filled. So hydrogen can form one covalent bond, which it does. Helium is a noble gas, so you would not expect it to form any covalent bonds. Well, if we go through this analysis, it has two valence electrons, but its valence orbital, the 1s orbital, only has a capacity of 2 electrons, so therefore that orbital is filled. Helium has no available orbitals, and as a result, can form no bonds. Moving down to the next period, lithium behaves just like hydrogen does. It has a single valence electron, and in this case now it actually has 4 available orbitals, because when you're in shell 2, we have the 2s and the 3 2p orbitals. So there are 4 available valence orbitals in shell 2. So obviously it has fewer valence electrons than available orbitals, so it can form only one covalent bond. Moving over to beryllium, it does have 2 valence electrons, but it still has 4 available orbitals rather than 0. Well, it has 4 valence orbitals and it has 4 available orbitals because none of them are completely filled. Therefore, beryllium can form 2 bonds. Okay, boron, 3 valence electrons, 3 bonds. Carbon, 4 valence electrons, 4 bonds, because in both of these cases, just like with lithium and beryllium, we have 4 available orbitals. The situation changes when we move to nitrogen. Okay, so nitrogen has 5 valence electrons, but there are only a total of 4 orbitals in shell 2. So if we have to put 5 electrons into 4 orbitals, we have to pair 2 electrons into 1 orbital. And you can see that on the figure here. So one of those orbitals has 2 dots next to each other, and then there are 3 dots by themselves on the top of the left and the right of the nitrogen atom, and that shows that those are half-filled orbitals, and therefore they are available orbitals. So nitrogen has 5 valence electrons, but only 3 available orbitals, so therefore it will only form 3 bonds. This situation continues as we move further to the right across the period. So oxygen has 6 valence electrons, but 4 of those are paired up in 2 pairs, and only 2 of them are in half-filled orbitals. So as a result, oxygen has only 2 available orbitals, and oxygen will only form 2 covalent bonds. Fluorine has 7 valence electrons, but 6 of those 7 are paired up in 3 electron pairs, and 1 of those electrons is by itself. Therefore, fluorine has 1 available orbital and can form only 1 covalent bond. Okay, neon, just like helium, is a noble gas. All of its entire shell is filled. It has no available orbitals, so it can form no bonds. And if you just continue looking down, sulfur, selenium, tellurium, etc., you get the same situation moving further down a group as you do higher up. The difference is, and we'll see this in a later lesson, as you move down a group, you actually are going to have more than 4 valence orbitals to work with. So we will have the possibility, as you start to get into period 3 and below, of forming more covalent bonds. Okay, so let's look at a typical problem, which would be to draw a correct Lewis structure for the formula H2O. Okay, I know this is a really simple example, but I still want to go through the truly rigorous way to solve this problem, and then we'll get into a shortcut. So the first step is to determine the total number of valence electrons for the molecule. So what we do is we go element by element, and we plug into, you can make a table if you want to, you plug in how many atoms of that element you have in the formula, and then how many valence electrons that element comes up with from the previous diagram on the previous slide, multiply those two together, and that gives you the total number of valence electrons from that element. Okay, so there are 2 hydrogens, each one contributes 1 valence electron, so there's 2 total valence electrons coming from the hydrogen. For oxygen, there is 1 oxygen atom that is contributing 6 valence electrons, so we get 6 total valence electrons from oxygen. Now add together the right-hand column, and we get a total of 8 valence electrons. Okay, so then we want to use as many electrons as possible to form chemical bonds between the atoms. And just as a hint here, you'll have a greater chance of success of coming up with a correct structure if you put the atoms that form more bonds closer to the center of your structure. In fact, if you have a structure like this that has just 1 heavy element and 2 hydrogens, that element in the center of your structure is what we call the central atom. Okay, so oxygen is going to be our central atom, and we want to put as many electrons as possible in bonds. Well, we know that oxygen is going to be able to form 2 bonds, so there's 2 bonds. And we're going to put the hydrogens at the other ends of those bonds. So that takes care of 4 of the valence electrons. We need to get up to 8 valence electrons, and we're going to assign all of the remaining ones as lone pairs where appropriate. Well, hydrogens, remember the electrons in the OH bonds count towards both elements. So hydrogen already has 2 electrons. Each of those hydrogens have 2 electrons. So hydrogen is already satisfying the octet rule. But oxygen in the structure as drawn only has 4 electrons around it. So we need to add 4 more electrons as 2 lone pairs in order to get its electron count up to 8. And luckily, we have enough valence electrons total to make it all work. Okay, so then step 4 is going to be to check your work. Is each atom forming the correct number of bonds? Yes. Oxygen's forming 2, hydrogen's forming 1. Do you have the proper number of valence electrons in your structure? Yes. There are 8 of them. So we are good. Okay, so the shortcut I promised you. So frequently on a problem, and especially as you move on into organic chemistry, you're not going to have time to calculate the total number of valence electrons and make that nice table I made. So if you remember the following for uncharged atoms, you'll be able to solve these problems faster. And this just comes off of the table on the first slide of this lesson. Hydrogen forms 1 bond, carbon forms 4, oxygen has 2 bonds and 2 lone pairs, nitrogen 3 bonds and 1 lone pair, and the halogens, fluorine, chlorine, bromine, iodine, usually get 1 bond and 3 lone pairs. That's always going to be true for fluorine. There are some examples as you get lower down in the halogens where we have more orbitals to work with that we can actually do other things with them. Okay, so let's do another example and use the shortcut method. Okay, so the compound that we want to draw a Lewis structure for is nitrogen trifluoride. So we'll start by making nitrogen the central atom because it's going to form the greatest number of bonds. Okay, so we know if we look at our table, nitrogen gets 3 bonds and 1 lone pair. Okay, so I'm going to draw 3 bonds and 1 lone pair off of the nitrogen. And then you're going to add the fluorines. Fluorines get 1 bond and 3 lone pairs. So we're going to add the fluorines to the ends of these bonds and give each one of them 3 lone pairs. And that turns out in 2 steps is our correct structure for nitrogen trifluoride. And we can always check our work by adding up the valence electrons and making our little table, right? There's 1 nitrogen, gives 5 valence electrons, so there's 5 coming from nitrogen. There's 3 fluorines, Each one has 7 valence electrons, so that gives us 21. Add those together, and we should have a total of 26 valence electrons. So that's coming from the atoms and their elements. Now, if we look at the structure, the Lewis structure that we drew for this molecule, we're going to count this up a different way. We're going to look at how many bonds there are. The answer here is 3. Each bond is a source of 2 electrons, so that means that there are 6 electrons in the bonds. There is 1 lone pair on nitrogen, so every bond is 2 electrons, every lone pair is 2 electrons. I didn't make an explicit column for that in this table because that's always going to be true. There's 1 lone pair on nitrogen, so that's 2 electrons. There are 9 lone pairs on fluorine, right? 3 fluorines, each contributing 3 lone pairs. So there's 18 electrons coming from the lone pairs on fluorine. Add up the numbers in the right-hand column, and we get to 26. As long as you get the same number of electrons counting both of these ways, you've done the problem correctly. Okay, so that's Lewis structures of simple compounds. Then in the next lesson, we're going to get to Lewis structures of more complex molecules.